Hi, I'm Professor Goins, and welcome to the Math Professor's YouTube channel. If you find the content to be useful or interesting, please consider subscribing. Also, any quick and easy interactions you can give us, such as liking our videos, commenting on our videos, sharing our videos, would be appreciated because any of those things would help us grow. Let's go ahead and get into the video. What I want to talk about is the limit definition of the natural base. If you've taken multiple math courses, you probably noticed that this number e appears all over the place. For example, in your pre-calculus class, you'll see it as population growth and exponential decay, in particular carbon-14 dating. If you're taking the statistics course, you've seen it come up in probability as the function that's related to the normal distribution. In other words, the bell curve, that graph, is based on the number e. Taking the differential equations course, you'll see that it's the natural exponential function, which of course has base e, is a solution to this fundamental differential equation, and so on and so forth. This comes up in pretty much every math class you'll take. Why is it so important? Where does it come from? Well, again, since it comes up in all those different contexts, it's probably a pretty important number to understand. Let's go ahead and let's get into some details of what this number is. Well, pi is this famous number. It's approximately 3.14159. If I was to say, introduce you for the very first time and say, pi is this important number and it's approximately 3.14, you'd say, okay, great. What does that even mean? Well, we dig a little bit deeper and we recognize that the definition of pi is the ratio of the circumference to the diameter of a circle, which happens to be approximately 3.14159. So that gives us a little bit more of a context of what the number represents. Again, it's related to a circle. A lot of times in, say, a pre-calc class, we'll introduce this number e when we talk about exponential functions, and therefore the natural exponential function. And your instructor might say something along the lines of, e is this important number, and it's approximately 2.71828. Your calculator knows what it is, so it's just this number. Well, what I want to do is I want to dig a little bit deeper, and let's see where this number comes from. How is it represented? Things like that. So yes, it is approximately this decimal expansion, but okay, great. What if I said, I made up some number and I said gamma is approximately 4.2916, and I called this the Goins number. And you say, okay, well, great, what is it? It's just the Goins number, right? So that tells you nothing about it. So what I want to do is, again, I want to dig a little bit deeper into what the number actually is. All right, well, it's a real number, and let's take a look at the entire set of real numbers. I can partition, meaning I can separate it into disjoint sets as rational and irrational numbers, right? Every real number is either rational or irrational, and there's no number that's both. For example, of course, rational numbers would be things like 2, 4/3, negative 1/5, etc. In other words, a ratio of integers. Irrational would be things like the square root of 2, or pi, or e, etc. Those are irrational numbers, which means I cannot write these as the ratio of integers. I've heard before somebody said, well, pi can be written as pi over 1, so why is that not rational? Well, this is a ratio, but it's not the ratio of integers, so this is still irrational. Now, there's actually another way that we can decompose the real numbers, or in particular partition the real numbers, as follows. There's actually a sub-collection of irrational numbers that are called, and I'm just going to abbreviate this here, that are called transcendental, and then everything outside of that would be, say, algebraic. So algebraic would consist of everything that's out here. Now, here's what those numbers would represent. First and foremost, for example, I said that the square root of 2 is irrational, but consider the following equation. X squared minus 2 is equal to 0. Of course, if I solve this, I get x squared is 2, and therefore x would be plus or minus the square root of 2. So an algebraic number is the solution to an algebraic equation. For example, the square root of 2 is irrational, but it's the solution to an algebraic equation, meaning it's an algebraic number. Of course, any rational number is also algebraic, because I could say, well, what about x squared minus 4 equals 0? That'd give you x squared is 4, so x would be plus or minus 2. Similarly for any other rational number. Every rational number is algebraic, but some irrational numbers are algebraic as well. Now, a transcendental number means there's no possible way that I can find this as a solution to, say, a polynomial equation. There's no polynomial equation like x squared plus 4x minus 5 equals 0. Let's even throw some other terms on there. Negative x cubed minus. There's no possible way that I can come up with a polynomial where the solution is e. That's never going to happen. Similarly with pi. Pi is also transcendental. So pi and e land in that set. Square root of 2 lies in this set, and let's say 2 lies in this set. So pi and e in particular, e is not only an irrational number, it's also a transcendental number. Okay? So again, this just kind of shows me or tells me where it lands within the set of the real numbers. Now let's get a little bit deeper into where this number comes up. Okay, so let me clean up the board, and then let's look at the number e as a limit. Let's consider the following limit. Now look at the expression 1 plus 1 over x to the x, and then as x goes to infinity. For those that are new to the limit concept, you might glance at that and say, well, the limit is 1. Because you say, well, as x goes to infinity, 1 over x goes to 0, 1 plus 0 to anything is 1, so therefore the limit is 1. But the idea is I'm not taking the limit of the inside first and then taking the limit of the outside. The limit is going at the same time. So 1 plus a half squared, 1 plus a third cubed, 1 plus a quarter to the fourth. And the limit is not 1. Well, what is it? Well, let's just call it L for the moment. Let's say this limit, if it exists, equals to this number L. Let's see what we can do with that. Well, in order to evaluate this limit, let's sort of get some motivation here. This exponent being a variable is sort of the problem with kind of computing this algebraically. So what tool do we have that will move an exponent? Of course, that'd be a logarithm. So let's take the natural log of both sides. Okay, all I did is take the natural log of both sides. Now remember, the natural log is a continuous function, and the limit operation is interchangeable with continuous functions, meaning I can interchange the operation of taking a limit, taking a log, writing this as the limit at infinity of the natural log that expression. And now I can take the natural log of this expression where take the exponent that's on the inside. I could bring that out front as a coefficient. Well, if I take the limit as x goes to infinity, let's see what we have. This factor goes to infinity. All right, well, what about this factor? As x goes to infinity, 1 over x goes to 0, so this would be the natural log of 1, which is 0, meaning I have infinity times 0. That would be an indeterminate form, and let's see if we can rewrite this so that way I can use L'Hopital's rule on it. Well, if I rewrite x, so first and foremost, keep in mind off to the side here, of course, 2 is the same thing as 1 divided by a half, right? This could be anything, and then I just take 1 over that number. Therefore, I'm going to rewrite this expression as the limit x goes to infinity, natural log of 1 plus 1 over x, all over 1 over x, right? X can be written as 1 over x, just like 2 can be written as 1 over a half. And this, of course, is equal to the natural log of L. Now let's look at this limit here. Does this have an indeterminate form for which L'Hopital's rule would apply? X goes to infinity, 1 over x goes to 0, natural log of 1 is 0. As x goes to infinity, 1 over x goes to 0. So this has indeterminate form 0 over 0, meaning I can use L'Hopital's rule, differentiating the top and the bottom independently, and then taking the limit of the corresponding result. All right, so the limit of the numerator, remember the derivative of the natural log is the reciprocal of the argument times the derivative of the argument. And then this would be divided by the derivative of 1 over x, which is negative 1 over x squared. And again, that's equal to natural log of L. Now notice what happens. Those two factors cancel. Okay? Cleaning that up, this gives me the following. The limit x goes to infinity, 1 over 1 plus 1 over x is the natural log of L. As x goes to infinity, 1 over x goes to 0, giving me 1 over 1 plus 0 equals the natural log of L, meaning the natural log of L is 1. Solving that equation, or knowing that the only number whose natural log is 1, gives me L is E. So therefore this limit here is E, and that's generally taken as the definition of the number E. Let's say E is defined to be the limit as x goes to infinity, 1 plus 1 over x to the x. One thing this allows me to do is I could get a pretty decent approximation of E by just taking my calculator and plugging in a large value of x. For example, let's say I was to take x equal to, let's just say 100. Then E is approximately 1 plus 1 over 100 to the 100th. And what does that give me? Okay, I get approximately 2.7048, etc. And of course, as I take larger and larger values of x, this approximation will get closer and closer to the decimal I gave you at the beginning of the video for E. If I look back at this work, I could slightly generalize this. And suppose I change this numerator here to an A. Then let's kind of trace through what happens with that number. If that was A, then that would be A. This would be A. 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 Negative 1 over x squared, negative 1 over x squared still cancels, but the a does not, meaning this would be a. This would be a. And if the natural log of L is a, then L would be e to the a. This is probably listed in your chapter on sequences and series as a common limit, or perhaps in the section for when you introduce the natural log and natural exponential function in your calc book as well. Okay. Now there is also another definition of the natural base that you'll probably see in your calc book, and what I want to do is I want to do this a little bit more informally, but I'm going to start with this right here and kind of do one of these ideas where I'm going to take the approximation and I'm going to rearrange the terms. So again, this approximation here sort of motivates the following manipulations. If e is defined to be this limit, then for large x, we know that e is approximately 1 plus 1 over x to the x. Think about taking, rather than x equal to 100, what if I took x equal to 1,000,000 or 1,000,000,000 or 1,000,000,000 or just some extremely large number, maybe one with 100 zeros behind it, right? Then it just makes this approximation get better and better. What I want to do is I want to rearrange the terms here. If I take both sides to the 1 over x power, I get e to the 1 over x is approximately 1 plus 1 over x. Now what I'm going to do is I'm going to do a change of variables. I'm just going to say h is equal to 1 over x. If x was really, really large, so x is, say, 1,000,000 to the 1,000,000th power, just some really large number, then that means that h is going to be approximately 0. Okay, so now if I rewrite this, I would have e to the h is approximately 1 plus h. Therefore, e to the h minus 1 would be approximately h. Then if I divide both sides by h, I get e to the h minus 1 divided by h is approximately 1. And this is, again, for h really, really close to 0. And this gives me my second definition of the natural base e, and you'll probably see the following in your textbook. They'll say e is the unique real number satisfying the limit as h goes to 0 of e to the h minus 1 over h is equal to 1. Meaning if I change this base here to any other real number, this limit would not be 1. But e is the unique real number for which this happens. This limit definition of e is the one that you will use when you first look at the derivative of the natural exponential function e to the x by using the limit of a difference quotient. And that's where it comes from. Okay. Thanks for watching, and please don't forget to subscribe.